Hello, my name is Morissey from the Level 6 Creative Computing class, and this is my handwritten number classifier model for the machine learning subject. So to start, I imported the required libraries such as TensorFlow for building deep learning models, NumPy for numerical operations, Matplotlib and Seaborn for data visualization, and Gradio for creating the user interface, which I'll be showing later. The dataset used for this project is the MNIST dataset, which is a dataset that was created by remixing the samples from the NIST original dataset. It contains 70,000 grayscale images of handwritten digits, with each image being a 28 by 28 pixel array with corresponding labels from 0 to 9. I then used TensorFlow's class.dataset.mnist to load and split the dataset into training and testing sets, with the training set containing 60,000 images and the testing set containing 10,000 images. As for data visualization, both the training and testing sets are printed using the shape function, along with the first 9 images from the training dataset. Additionally, I also printed the raw pixel values of the first training image to use as a reference between the raw pixel values and the values that I'll be normalizing in the data normalization. Now for data normalization, the values of the images are normalized to a range between 0 and 1, and this is done using the scale images function, which divides each pixel value by 255. And additionally, the normalized pixel values of the first training image was printed to verify the transformation. And as you can see here, there is a difference when you look at the scaled values versus the raw values. Now moving on to the model building, I used TensorFlow's sequential model with the ngModel function defining its architecture. And the model begins with an input layer that specifies the input shape as 28 by 28 by 1, representing the 28 by 28 grayscale images with a single channel. And defining the input shape ensures that the model knows the dimensions of the incoming data. Now, the first layer is a convolutional 2D layer which applies 32 filters with a kernel size of 3 by 3, and this is to scan the input image and detect basic features like edges and corners. And the activation function here is ReLU, which is a rectified linear unit, and this introduces a non-linearity, and it helps the model learn complex patterns. And next is the max pooling 2D layer, which has a pool size of 2 by 2. And this layer reduces the size of the feature maps by retaining the most important features. And it makes the model efficient while also preserving the key information. And next is another convolutional 2D layer with 64 filters and a kernel size of 3 by 3. And this is to extract more detailed and complex patterns such as curves and final details in the digits. And this is followed by another max pooling 2D layer, which again reduces the size of the feature maps and ensures that the model focuses on the critical features. And then the flatten layer, it then converts the 2D feature maps into a single one-dimension array, which is necessary to pass the data to the fully connected layers. And then the first dense layer is a fully connected layer, as mentioned earlier, with 128 neurons, and it also uses the ReLU activation. And this layer combines all the extracted features to learn complex patterns and relationships in the data. Finally, the output dense layer has 10 neurons, one for each digit class, which is 0 to 9. And the activation function is a softmax, which converts the raw outputs into probabilities with the highest probability indicating the predicted digit. And then the summary function prints the overview of the model's architecture. and then the function returns the completed model. And then after that, the input dimensions are determined using the shape of a single training image, and the number of output classes is set to 10, representing the digits. And then the image model function is then called with the input shape and the number of output classes to create the number classifier model. Now for model training, the model is compiled with the Adam optimizer, which is known for its efficiency and its ability to adjust learning rates during training. Then I use sparse categorical cross entropy for loss since it works best with multi-class classification problems, and then using accuracy as the metrics. The model was trained for 20 epochs, and this number was finalized after I experimented with values between 10 and 30 epochs to balance accuracy and overfitting. And as a result, 20 epochs was the one that gave me the best results while I was experimenting. Now, for model evaluation, the model is evaluated on both the training and testing datasets to measure its performance. The evaluation includes plotting accuracy and loss graphs over 20 epochs to visualize the training process. And then I printed the final training and testing accuracy scores to verify the generalization. And as you can see here, the testing accuracy is 99.12 and the training accuracy is 99.93. And after that, I also generated a confusion matrix to identify areas where the model performs well and which areas need improvement. And as you can see here, the confusion matrix revealed high accuracy, but it also has some minor misclassifications between similar digits. So for example, 9 and 4. Now, as for testing, the model's predictions are also tested based on sample images from the testing dataset. And I did this by just printing a random number from the testing dataset. And then after that, I proceeded with printing a 3x5 grid of the first 15 samples from the testing dataset, along with their predicted and true labels. And as you can see here, the predictions matched the true labels with high accuracy, and this proves the model's reliability. So as you can see here in the 15 images, here are the predicted labels as well as their true labels, and none of them have a mismatch. Now, in order to make the model interactive, I developed a Gradio interface where users can draw a single digit on a sketchpad, and then the users receive the prediction result along with a history list of their past predictions. And during development, I had to downgrade the Gradio version due to a bug. So as of now, I'm using version 3.50.2. But nevertheless, the GUI and the model still works. So here, the predict image function processes the user drawn image by reshaping and normalizing it to match the model's input requirements. And then the model predicts the digit by identifying the class with the highest probability. And then a global list tracks the prediction history and displays it alongside the current prediction. And then additionally, I also added a small CSS script just to customize the background color. Now I'll be showing you how it works. And as you can see here, this is what the final GUI looks like. And here is the input, which is the Gradio sketchpad, and the output, which is the prediction and then the prediction history. Now, for example, if I draw a 1, click submit, and as you can see here, prediction, the predicted drawn number is 1, and then the predicted history or prediction history, the first result, it shows that my first result is 1. So for example, if I draw a 4, it shows a 4. The predicted drawn number is 4, prediction history, result number 2 is 4. And if I draw more numbers, so I can show the prediction history, as you can see here, it saves the predicted numbers, a list of the predicted numbers. Now, going back to the misclassifications, for example, if I draw a number 4, it can still say a 4. If I do this way of drawing a 4, so it's a 4. But sometimes if I draw like 8, 9, in some cases it might say that it's a 4. For example, here, this is a 9, but then it says here that the predicted draw number is 4. And this could be due to problems in the dataset, since although it's been used a lot of times, it's not fully accurate, or sometimes it's also because of overlapping characteristics between numbers, which can result in making the model confused. And yeah, that's about it for my walkthrough video. Thank you for watching.